Okay, students, let's talk about the Pinacol rearrangement. The Pinacol rearrangement converts 1,2-diols to carbonyl compounds via acid catalysis. So specifically, the carbonyl compounds that are converted, or that the 1,2-diol is converted to, is ketones or aldehydes. And the catalyst that is commonly used is sulfuric acid. So let us take a look at how this looks. Okay, so we'll have a 1,2-diol, or also what we call a vicinal diol, or is also called a pinacol, hence the name. So here we are, and I'll just draw in those lone pair electrons because they are important in this reaction. And ultimately what we would get here from the Pinacol rearrangement is 3,3-dimethyl to butanol. Yeah, here we go. Okay, so we can see we went from this 1,2-diol to this ketone. This would be 3,3-dimethyl butane. I'll do it the contemporary way, butane 2-on. And this would commonly be called pinacolone. And this, of course, if we name it, this would be 2,3-dimethyl butane 2,3-diol. And this here is called the Pinacol, hence the term Pinacol rearrangement. Now, if we view the mechanism behind this reaction, I did forget my acid catalyst here, sulfuric acid. If we view the mechanism behind this reaction, we can get a glimpse as to what's going on. You can see from the reactant, from the diol to the ketone, that we got some methyl shift occurring. We have an OH group that is left, and one of the OH groups has lost a proton and thus formed the oxygen double bond here. So in order to get a glimpse into what's going on, let's look at the mechanism behind this reaction. I'm going to draw this a little differently than what we have above here. So I'm not even going to draw CH3s. You know how we represent CH3s in the line angle drawing. So I'll just draw a line for the CH3s. So here, and we'll draw this here, and we'll draw another methyl here and another methyl here. Now, of course, you know that the acid provides us a source of hydronium ions, which is our acid, and one of the protons is very acidic on the hydronium ion, and so the oxygen lone pair we'll extract that proton, and the electrons that are shared between the hydrogen and oxygen will go on the oxygen to thus form water. And what we get from that is this species that we've been talking about quite a bit. So we protonate the OH group to form the water species. Alright, so what's going on here? Well, why you didn't protonate the other OH group? Well, this is what we would call a symmetrical diol. Alright, 1,2 diol. And so in a symmetrical 1,2 diol, it doesn't matter which OH group you protonate. Alright, so long as you protonate one. Okay, and so of course this is water. It leaves, and we thus form our good old friend, that tertiary carbocation in this case. So I'm going to draw a tertiary carbocation here. Okay, so what will happen is we will get a methyl shift to this. Of course, we lost water here, and we'll utilize water later. All right, so once we get that methyl shift occurring, what you'll begin to see is that we're almost at our product stage, getting really close now to the formation of our product. Okay, oh crap, we did the methyl shift, so I need to erase this. Alright, so you may be thinking, okay, well look, we had a tertiary carbocation that was fairly stable. Now we've created this carbocation. But if we look deep into the resonance structure here for this, so that is, I'm going to draw a resonance form for this. So what's going to happen is the lone pair on the oxygen is going to kick down to form a double bond. And we have a positive charge now on the oxygen because it's still bearing the proton there. Which one of these would be our major component, our major contributor, resonance contributor, and which would be our minor? Well, think about what we discussed in Organic Chemistry 1. What we see here is that the carbon here bears a positive charge, so the octet isn't complete. So this would be our minor component. What we see here, the oxygen bears the positive charge, true enough. But if you look at the octets, all the octets are complete. And so this we would call our major component. And this is really the driving force for this reaction. Now remember water? Well, water makes another appearance. Okay, so this proton on the oxygen here is fairly acidic, and so water can act as a base and extract that proton, and thus the electrons that are shared between that proton and oxygen will go on the oxygen. And voila, we have our product here. So here's our Pinacol product, our ketone, alright, our 3,3-dimethyl butane 2-one that is formed from our Pinacol here, or our 2,3 dimethyl butane 2,3 diol. And again, for symmetrical diols, it doesn't matter which proton is protonated here. Of course, because we use the acid catalyst, the hydronium ion is, of course, regenerated. Remember, a catalyst is not consumed in the reaction. Follows zero order kinetics. So this is just one example of Pinacol rearrangement of 1,2 diols to form, in this case, a ketone with a sulfuric acid catalyst. And the next video we will look at what's the situation with unsymmetrical 1,2 diols and using sulfuric acid catalyst. So until the next video, happy studies.